Hi, how's it going? This is the 5th installment of the organic chemistry videos I've been doing. Today I'm going to talk about stereoisomers, or enantiomers, is one of my favorites. And we're going to talk about how on the exam to rotate them in your mind and figure out which one is the RR isomer and which one is the S isomer. And we're going to also talk about L and D in biochem. I don't know why in organic chemistry we use R and S, and then suddenly when you go to biochem you use L and D. It means essentially the same thing, but anyone can explain that to me, that'd be great. But let's go to the marker board and start talking about isomers. Alright, so essentially an enantiomer is a mirror image. We'll use... This is an example. I'll just put these halogens on here. Iodine, hydrogen. Now, we'll use an expression called a chiral carbon. Chiral just means that it has the possibility of an enantiomer. So any carbon with 4 different substituents is a chiral carbon. If I had this as a structure, this would not be a chiral carbon because I have 2 of the same substituents, and I cannot have an enantiomer unless all 4 substituents are different. So if I draw the mirror image of this, look like this. Now at first glance you would think if I just flipped this, because we said that let's see, like if we did this molecule, so if we did propene, this would be the same exact thing as a propene molecule like this. And you might say that this is the same if I flip it, but if you check it out, there's no chiral carbons here. This carbon is double bonded to the CH2 here, and there's no chiral carbon here, no chiral carbon there, no chiral carbon there. So as long as you don't have a chiral carbon, there's no possibility of an enantiomer. So if you flip this, yeah, it's the same thing as this. But with this, it's kind of like your right and left hand. You can't superimpose your hands on top of each other like this, because they're mirror images of each other. So let's draw this in a 3-dimensional structure, shall we? So we'll picture the iodine is going to be on the plane of the board. The bromine is going to be coming out at us. Chlorine is on the plane of the board, and the hydrogen is going in back of the board. So we have a 3-dimensional shape. If you look at the iodine, the bromine, and the hydrogen, they're kind of like this, and the chlorine is coming off on top. So if I take this image and I rotate it here, the bromine is going to be here, and the iodine is going to be here. So it's not superimposable. Now, you might think, what's the big deal? Because you're going to have an equal ratio of these enantiomers when you make a product with a chiral carbon. Actually, I don't know what the drug was called, but in the 70s, there was a pill for morning sickness, or some kind of medication for morning sickness, and the one isomer of it actually cured the morning sickness, but the other isomer was a very powerful teratogen, which causes birth defects. I believe the drug was released in Germany, and all of the children had like these weird flipper-like hands. But it shows how much of a big deal the chiral carbon molecules can make, like in the pharmaceutical industry. But anyway, if we look at the substituents, we look at it in terms of like clockwise or counterclockwise. If it's clockwise, meaning like that, it's the R isomer. If it's counterclockwise, we say the S isomer. And this just means rectus and sinister. Rectus meaning right, sinister meaning left. If you ever heard the old wives' tale that left-handed people are evil or sinister, that's where that comes from. But we're going to look at that in terms of the most important. So iodine is going to take precedence and then bromine, and then chlorine, and then hydrogen. So since the hydrogen is least important, we're going to spin that around to the back of the plane, and we're going to go iodine, bromine, chlorine. So if we look, it's going this way, clockwise. So this is the R isomer, and here we have iodine, bromine, and again the hydrogen is going to be turned. We're going to have the chlorine. So this is the S isomer. In organic chemistry, we use R and S. In biochemistry, use L and D. D meaning dextrose, which is right. Someone's sending me an instant message. Why? Let's sign offline. I apologize. We use R and D. I'm sorry, L and D. The L is the left and the D is the right. I believe it's dextrose, and L, my Latin is rusty. But anyway, let's do alanine, which is one of the most simple amino acids next to glycine. So we have NH2, CH, CH3. Alright, so here's alanine. If you look at the chirocarbons, this is a chirocarbon. This one is not, because you have this carbonyl oxygen here. So if we look at alanine, the enantiomer of it is going to look like this. So I believe this group would take precedence, followed by the amide group, followed by the methyl group. So if you look, this is going to go counterclockwise. This would be the L, and this would be the D. This one would go clockwise. So it's just right and left hands of the same molecules. Very interesting stuff. And as I said, so I was talking about that drug in Germany that was released like 30, 40 years ago. Like, enantiomers do make a big difference in the pharmaceutical industry. But I hope this clears up any questions you might have on the exam about enantiomers. Your professor will probably give you a series of structures like this and ask which one is the L and which one is the D. If you just use common sense and figure out which group takes priority over the next, like, obviously these two oxygens, and the carbon is a very big bulky group, has a lot of important molecules in it, or atoms in it, whereas the amide group would be second in priority, followed by the methyl, and then the hydrogen is always least in priority. So usually you take that to the back of the plane and you would rotate it according to the other substituents. But I hope this helps out, and thanks for watching.